All right, so good morning, everyone. Welcome back. Thanks for being still here. So today my plan is to conclude our study of this problem of statistical inference that we started to look into. I'll start by reminding ourselves what the setup is. So in the beginning, we have this unknown vector x bar made of n IID coordinates, x bar 1 up to x bar n. I write the law of this guy Pn. And from that, we observe the following thing. So we call it y. It's some scaling factor times the matrix x bar transpose plus standard Gaussian noise. Like this is a matrix with IID entries, standard Gaussians. And yesterday, we argued that it would be good for our analysis to consider a more general situation in which we observe not only this, but also a simpler observation, which is directly linear in terms of x bar. So I think I wrote it y tilde. It's just square root of 2h, x bar, plus some other noise, which I denoted by z. Okay, again, independent standard Gaussians are the coordinates of the vector z. And the parameters t and h are just parameters we can play with. So in the end of the day, we may be mostly interested in the case when h equals 0. But we consider the more general case in order to facilitate our study of this problem. And one of the things we want to recover is the minimal mean square error. This is expressed in terms of the law of x bar given the observations. And we wrote this law like so. So when I want to, if I think of this variable x here as being sampled according to the conditional law of x bar given the observation, and this is taking the average with respect to this measure, then we had observed that this we can put in the form of something that looks like a Gibbs measure, okay, for some explicit function hn of t, h, and x. Okay, and let me emphasize that this is what is on the right-hand side is still a random quantity. Okay, you should really think of this as for each choice of x bar, w, and z, you can define this probability or this expectation here. Okay, so if you like, there are two levels of randomness. Once I introduce this notation, there's this kind of outer randomness when we decide what is x bar, what is w, what is z, and then I can take expectations with respect to the conditional law of the signal given this observation. Okay, and these new random variables we write with this x symbol, and this is expectation for that. Okay. Are there questions on this or? And I've been repeating this over and over again. And on this problem as well, I want to study the free energy, which is the function that computes basically the normalization constant in this expression. So Fn of t and h is log 1 over n log integral exponential of what is just written above. And unlike the Curie-Weiss model, in this case, this free energy, as I have written it here, is random. So I also want to consider the average, which we write Fn bar of t and h. Okay, and yesterday maybe I won't rewrite again the whole expression for hn of t, h, and x. But yesterday we've seen that we can write it down, of course, and also that using this expression we can calculate derivatives of this function with respect to the parameters. And in particular, we found that when we differentiate with respect to t, we find what we could call the square of the overlap, if we want to use that word. Anyway, the scalar product between the original signal x bar and this random variable x that we sampled, as I said earlier, squared, while when we differentiate with respect to h, we find just the mean of that guy, okay, with no square. And so, like in the Curie-Weiss model, we think that maybe if this random variable has a small variance, then in the limit of large n, the t derivative will be the square of the h derivative. And we would like to justify this. So let me write that relationship again. And maybe instead of writing variance like yesterday, I'm going to explicitly write the difference of the squares so that we are not too confused. And maybe I'll write like this. Minus like so. Okay? So it looks like it is a variance with respect to these two layers of randomness at the same time. And yeah, we would like to do the same sort of program as for Curie-Weiss and justify that as n goes to infinity, this in some sense goes to 0, and therefore Fn bar solves the PD that is written on the left. And another thing that we may be interested in, if we have this program in mind, is to make sure that we can calculate this function when t equals 0. So I did not write the full expression for hn of t, h, and x, but at least I'll write it when I set t equals 0. So Fn bar of 0 and h is, okay, there's 1 over n, expectation, log, integral, exponential of square root of 2h z dot x plus 2h x dot x bar minus h, yeah, maybe x square, and then everything is against dpn of sigma. Correct? Okay, so hopefully I got the expression right. In any case, the point I want to emphasize here in this expression is that, you know, imagine you write everything in coordinates, like all of these scalar products. You write sum of zi xi, sum of xi x bar I. I wrote sigma, but I meant x. You see that it's, and this is sum of xi squared. You see that it's really, you can write the whole thing as just a sum over I, and then the indices are not interacting with one another. And this we postulate to be a product measure. So you can really, and okay, exponential of a sum, then you can write as product of exponentials. So you can really rewrite this integral as a product of n integrals. And then you take the log, okay, so it gives you the sum of these integrals. And then you take the expectation, but each of these terms have the same law. So in fact, this whole expression, again, does not depend on n. Okay, so this equals, so long conversation to just say that this is equal to f bar 1 of 0h. And maybe just to keep same notation as before for Curie-Weiss, I could call this function psi of h. Okay, so at least as far as the initial condition, as we could call it, is concerned, no problem. We can really describe it. It's a simple function. Okay, so the question now is, how do we justify that indeed, as n goes to infinity, this is going to converge to some nice PDE? In the Curie-Weiss model, we had managed to express this term as the second derivative of our free energy, multiplied by a factor of 1 over n. Now, in the setup that we are exploring currently, things are a little bit more complex, but essentially the same is going to occur. So I'm going to state this as the theorem. We have it. Okay, so clearly this is non-negative. So I write, in fact, something that looks very much like what we're used to. Okay, so this we're familiar with. That was the same for Curie-Weiss. But here there's a second term, which talks about the difference between the derivatives of Fn and of Fn bar. Okay, and perhaps I used a slightly informal notation. This, I mean, everything is evaluated at a given point. Okay, so at each point th, that inequality is valid. Good? So, of course, there could not have been an expression like this for Curie-Weiss because the free energy was deterministic. So here we're really talking about the fluctuations of Fn and Fn bar. Let me see if I made something. I think this is what I wanted to say. So perhaps I only give you a heuristic idea of how you prove this instead of giving you a full proof. But I claim once you understand what moves you should do, the full proof is not very complicated. So let's say idea of proof, or ID, maybe barely of proof, but one thing we've seen for sure is that, so we know what that is, okay? This is the variance of this random variable x dot x bar over n. And we've seen that this guy, for instance, is the, perhaps, let me explain this a bit better. Or change my strategy for explaining it. So we have this variance to investigate, let's say, to try to rephrase in terms of the free energy. And there are these two layers of taking expectation. And one thing we can do is just split these two layers one at a time. So perhaps I'm going to write this as x dot x bar over n, which I compare with just the Gibbs average. Oh, and then I should take the expectation outside here. So that's one term. And then another term would be comparing that Gibbs average with the full average. I'm not writing this properly. Okay, I hope I did this properly now. Sounds good? Okay. Yeah, so I would like to kind of try to argue that now we have these two terms, and basically they try to capture each of these two terms. So one thing that is for sure is that these two terms, they are the same. These are equal. Okay? And well, this is where my argument is going to be sketchy instead of being a proof. But you see that this guy is what happens when I remove the expectation of this guy. And so maybe this guy looks like this guy. Okay, so this is not true. Okay, this is you have to play with Nishimori to see exactly what's going on. But you should think that there's some relationship between these two things. These guys want to sort of resemble one another. Okay, so really this term you should match with that term. And similarly for this guy, again, this is not exactly correct, but we have seen for Curie-Weiss that when we take the second derivative, this calculates a variance for you. And it's the variance of that random variable whose expectation you're calculating when you calculate the first derivative. So again, this is not quite exactly correct, but these two things, they want to relate to one another, okay? This is the structure. Now, in truth, you have to just walk through your integration by parts, just the way we've done for calculating the derivatives. But this is what you get in the end of the day. So that will be it for justifying this theorem. Maybe I'll erase this as well. All right, so yeah, one comment I want to make first is that this model is really very analogous to the Curie-Weiss model, the standard one. But in general, when you consider more complicated statistical inference problems, you will not always be guaranteed one of the inequalities like we have here. For instance, if you decide that you observe a rank 1 matrix which is not necessarily symmetric, you're not going to have this beautiful inequality for free. So what you're going to get instead in general is that, so let me write it like this. You're going to get an inequality that looks much more like what we got for the generalized Curie-Weiss model. Like you just have absolute value smaller than the same sort of terms. Okay, so same right-hand side, but you have just absolute value here. And as I try to argue on, okay, maybe very briefly, but when we handle the generalized Curie-Weiss model, it is indeed a technical difficulty to deal with the fact that you have absolute values here. Okay, that the Laplacian maybe has the wrong sign, etc. And so for this model of statistical inference we're discussing, we won't have this problem. The inequality on the left looks very nice. We have it for free. But if you want to do the general model, you will have again to use these special techniques that I only very briefly discussed and that were concerning the generalized Curie-Weiss model, where you want to exploit the convexity of the free energy to help you. And one more comment I want to make for the general case is that now that when we define the free energy, it's no longer so simply a log Laplace transform of some random variables. You know, there are some square roots that are around, etc. So the convexity of the function is no longer so easy to obtain. Okay? So if you want to show that this free energy is convex, well, it turns out to be true, but you have to work through it. You know, you have to find the correct integration by parts again, or things like that to check that this is correct. And yeah, so because we are handling this simpler model, we won't have to face this difficulty. But if you want to do the general thing, you'll have to have a lemma at some point or something that asserts that the free energy is convex. Otherwise, at least I don't have another proof strategy for handling the most general case. OK, so now the key novelty in the problem is to understand how to handle this term. There are classical techniques to get statements that assert that something is close to its expectation. It's called concentration inequalities. So in the notes, we have written, I don't know, kind of fancy concentration inequalities to get sharp results on the concentration of the function fn around its mean value. But if you're not familiar with this, I also mentioned that at the end of the section on concentration inequalities, you have exercises on the F-Ronstein inequality and the Gaussian-Poincare inequality. And these will be enough for my purposes. Okay? I just want to say that Fn becomes kind of close to its mean as n goes to infinity. So let's say I want to assert that whenever you look at a compact set of parameters th, and you consider the difference between the free energy and its average, let's say to the power of 2, I just want to assert that this goes to 0. Okay, and maybe the sharp rate is, okay, at least one rate you can get with the things we do in the notes are like this. Maybe if you do F-Ronstein stuff, you get a less good rate. Maybe you'll get n to the minus 1 over 3, but I just want to say it goes to 0. Okay, so this you can get, let's say, for free if you already know about concentration inequalities. And if you don't, yeah, I think you should learn them. But this is about the function fn, not about its derivatives. So why don't I apply concentration inequality on the derivatives? Well, it's because it's not going to work, and it's not going to work for a good reason, is that sometimes there are indeed parameters at which this derivative is not going to look like its mean value. So what's going on? Well, perhaps we should not be too concerned about this, or at least I want to point out that it was already the case for this other term that we got used to dealing with, that there are indeed special points at which this term is not small. Okay, but we're handling this because we say, the definition of viscosity solution has a little bit of, let's say, margin to play with so that we can handle it. When we said that when we touch from above, this is not going to be big, and therefore when we touch from above, this is fine and everything is under control. So what I would like to say is that at this contact point, so when we touch from above, in fact, we can still say that this is under control. And perhaps one way you could get a first sense that maybe indeed this should be possible is that we've already seen a statement a little bit in this flavor some time ago when we said, if I have a sequence of convex functions that converge, and I look at a point of differentiability of the limit, then the derivative of the function converges to the derivative of the limit. Okay, and perhaps here we are also a little bit in this situation because I'm not going to use convexity of these functions, but I'm going to use at least that their second derivative is bounded from below. This is easier to check, even for Fn. And then we're going to touch them from above also. And yeah, okay, so hopefully we're going to be able to assert that the derivatives converge at the point when we touch from above. This is my goal for justifying not this theorem, but the next step, like the fact that as n tends to infinity, this tends to the viscosity solution. Maybe I'm going to state it. Let's say theorem. I said I use a French notation, so let me continue to do this. Okay, so this is what I want to show. There is another technical point which I'm not going to discuss. I gave you, I told you about viscosity solutions to equations that are posed with the spatial parameter being in Rd, but this H here is only allowed to be non-negative. It lives in R+, and I did not tell you exactly how you deal with that part. Okay, so in terms of touching from above and from below, I just think of it as the contact point now has to be in the interior of the domain here. So at least you have a definition of viscosity solution even on arbitrary domains. Okay, you just impose that the contact point is in the interior. Like I really mean in this open set. And then, yeah, what you don't have is a uniqueness statement for equations that are posed on this domain. And this can be shown, but I'm not going to give you a proof. And even in the notes, we use a little, instead of explaining this, we use a little trick, which is that if you give me, basically we extend the function to R+ by a reflection mechanism. We take the function, we take its symmetric around the origin to make it like even, and we show that the reflected function is a solution to the PD on the full space, just because it saves us a little bit of technicalities. But if you want to ask me about how you deal with the more general case, in fact, in some sense, we already did it, but with respect to the time variable when we justified the comparison principle. There was no boundary condition at the final time, And we did some trick to explain that this was still fine. And you can still do the same sort of trick for the h variable. OK, anyway, so this is what I want to show. And I'm going to especially focus on this. When we touch from above, we can justify the condition for being a viscosity solution.
So this PDE does not have a uniqueness.
Yeah, there is. So the thing is, I would have to. I think with the square, it's actually OK. I think it's OK like so. Ah, no, maybe not. No. If you want to have uniqueness, I would have to also add that f is non-decreasing, which it is because we have seen that the derivative is the expectation of the scalar product. And by Nishimori, I can also write this as x dot x prime. And this I can also rewrite as, let's say, 1 over n, expectation of the bracket squared. Okay, so this is non-negative. Because if you think about the reflection, if the function is increasing, it's going to look like this. If it's decreasing, it's going to look like that. You want to make sure that at 0, things point in the good direction. So yeah, you need to impose that sort of condition. But our function is like so it's fine. Other questions? OK, so before I prove this, I want to just record information about the second derivative of fn. So let's say note. So it's been, last time we computed the first derivative of fn before averaging. I'm going to rewrite the result here. So it's 1 over n. And then we have this 1 over square root of 2h z dot x plus 2 times x dot x bar minus x squared. Okay, so let me give a name to that thing. Hn prime of x, maybe. Maybe I'll just call it Hn prime. So this is, think about writing the free energy. You have log exponential hn TEH, and this is what occurs when you calculate the derivative in h of the energy function. Now this is a Gibbs measure, so you should picture in your head that you write it as integral of that guy exponential hn da da da, and I'm going to calculate the second derivative. So forget about the fact that there is an h here. Essentially, you're going to compute the variance of that guy. Okay, just as usual, when we compute second derivative of the free energy, we get something that looks like a variance. But there is a but. There is also this guy that still has an h, and so you have an extra little bit of junk, let's say, 1 over n, and then you have 1 over 2h to the power of 3 halves. Z dot x. Something like this. Okay, I hope I did not make a mistake, but I think this is what it is. So I want to have a lower bound on the second derivative. This might be big, but it's non-negative. And this is smaller than, in absolute value, than the norm of z times, so x is in the ball, so times square root of n, this is the bound on the norm of x. Okay, so what I want to record before I enter into the proof is that the second derivative, maybe I could write it somewhere in the corner. Oops. Okay, I'll write it. The second derivative is greater than minus 1 over 2h to the 3 halves times z over square root of n. Did I keep track of things correctly? Yes. So the norm of z typically, so this is a random variable, but typically it's going to be over the square root of n. So this is typically over the 1, and then I have a, it slightly wants to diverge when I approach 0, but essentially it's over the 1. I mean, it wants to diverge when h approaches 0, but as long as I stay away from 0, it's order 1. OK, so I'm erasing, but I'm going to use that inequality just now. OK, so let's turn into a, let's call it a partial proof of the theorem. OK, so first things first, we have seen the expressions for the derivatives of fn bar. And all of these expressions are obviously bounded. You know, x dot x bar over n is between -1 and 1. We're in this ball thing. And similarly for the second derivative. So our functions, as for the Curie-Weiss model, they are uniformly Lipschitz, independently of n. Okay, they are one Lipschitz. And also we have seen that when we set t equals 0, the function does not depend on n. So we are really in a good shape to apply the Arzelà-Ascoli theorem. We know that there exist converging subsequences. Okay, so let's say by Arzelà-Ascoli, the sequence of these functions fn bar is pre-compact. Okay, so I'm going to look at a converging subsequence and the limit along that subsequence. Let's call it f. And I want to show that f is a viscosity solution to the equation. So let's say let f be a limit along a subsequence. We want to show it's a viscosity solution. So I raised the inequality that I want to exploit, but one of the two inequalities was very easy. You know, we had just that equation greater than or equal to 0. So this will give us for free that the limit is a super solution. Okay, maybe I'm not going to explain it in detail, but at least I hope it's convincing that this is not going to be an issue. So let's say we can check that f is a super solution. We can check. I'm in a viscosity super solution. Okay, I don't always write the whole thing. So now we want to check it's a subsolution. Maybe I'm going to erase a bit of the board here before I start that. Or maybe I'll erase everything. Okay, so I'm going to want to use this, of course, but it's best if I erase it, I think. Maybe I'll just keep it. No, okay, so what do? We're supposed to take, let's say that th in 0 plus infinity squared, and let phi be a smooth function, such that f minus phi has a, and I may make it strict, local maximum at th. Okay, so I told you that when I'm in this sort of circumstance, I like to do a drawing a bit like this. You know, when I think that f maybe has corners and I'm touching it from above. However, in fact, f has this lower bound on the second derivative. So in fact, my drawing cannot really look like that, right? It's gonna be maybe more like, you know, maybe it has corners, but the corners can only be like so. And when I touch from above, surely I'm not going to be able to touch here. So maybe I touch from above like here. And you see that when I do my drawing, at the contact point, the F is actually going to be nice. There are not going to be any corner. There cannot be a corner from below, because that's how F is, and there cannot be a corner from above, because it's being touched by phi. And so the first step of the argument is going to just write this into equations instead of just doing a drawing. Where am I in this note? Okay, so perhaps first I'm going to say that we have the... And why do I care about justifying this? Is because I want to control this difference of the derivatives. Okay, so I want to, as much as I can, I want to say that the functions that are being touched are smooth. So as usual, we can find, so we're going to look at the contact point for the function fn bar itself instead of the limit. So we can find a sequence Tn Hn that converges to Th, such that for n large, fn bar minus phi has a local max at Tn Hn. An important point I want to stress is that we're assuming that these two parameters are strictly positive. So if n is sufficiently large, I know that these guys are also strictly positive. And if I wish, I can think that I take n sufficiently large that I know there is a little bit of a gap between Hn and 0, for instance. Okay, so I erased the bound of the second derivative here, but it had this 1 over h to the 3 halves. But I don't need to worry about it because I know that if I wish, by taking n sufficiently large, I'm staying away from 0 uniformly in n. Okay? So I'll just replace this 1 over 2h something by c. Okay, okay, ta-da. So we have this. So what can I say about fn bar? So maybe I should say, maybe I don't write, but from now on, I'm going to assume n is sufficiently large that this, especially Hn, is away from 0, uniformly in n. Okay, okay, so I'm going to use that. Okay, so let me write for every h prime smaller than, like a small constant, I can write that an increment of fn bar. So fn is the one that is below phi, so this is going to be organized like so. Okay, I just reshuffled the terms in the statement that fn bar minus phi has a local maximum at Tn Hn. Okay, move this guy to the left and this guy to the right, and you see this is what it says. Okay, so I restrict h prime to a small neighborhood because I only know local maximum in my hypothesis. The c is going to change many times in the argument, maybe, but just a large constant. Okay, maybe it's going to be larger and larger as we proceed, but that's fine. All right. So, okay, I can Taylor expand this. So this is smaller than h prime, the derivative of phi at the contact point, plus some error term, which is quadratic in h prime. Okay, another c that is showing up here. Okay, c is just expressed in terms of the second derivative of phi. Maybe it's an upper bound of the Hessian of phi. Okay, and we are at the contact point. We are not at the boundary. The T and Hn are both strictly positive. So that guy is the same as the derivative of fn bar. Okay, so I have, in some sense, a second order expansion of fn bar at Hn Tn with a good, maybe I should call this a C11 estimate or something. Maybe I don't write it again, but let me record here that this is equal to dh Fn bar of Tn Hn. Okay, maybe I try to erase a bit in advance. Okay, so we have this. Yeah, perhaps I should say also that in particular, the second derivative of Fn bar at Tn Hn is bounded by a constant. This is kind of obvious because you can say that because we are at a local maximum, the second derivative of Fn bar must be bounded by the second derivative of phi at the contact point. But you can also infer it from this development. All right, and now I want to record. I want to use the bound on the second derivative that I had written in this region on Fn. Okay, for h prime sufficiently small, the second derivative of Fn at Tn Hn plus h prime is bounded by minus c z over square root of n, right? So again, for h prime not too large, Fn of Tn Hn plus h prime minus Fn of Tn Hn minus h prime, the derivative, this is, sorry, I meant greater than. This is greater than minus c h prime squared z over square root of n. Agreed? I haven't yet made any sign mistake. Okay, so why do I write this? It's because I want to understand the difference between this derivative and that derivative, and I hope that by trying to express as well as I can that these functions are kind of smooth at the contact point, I can find a good estimate on the difference between these derivatives. So let's try to write it down. dh Fn minus dh of Fn bar at the contact point. So what did we say it is? Oh, there is an h prime in front, which I'm forgetting. Tac. Huh? Smaller than. So again, for h prime not too large, smaller than some C inverse. So what do I have? I'm going to have this difference of Fn's, and I'm going to have minus the difference of the Fn bars at the same points. So this I could just bound by, let's say, 2 times the supremum of Fn minus Fn bar in some neighborhood of Th. Okay, and let me call V this neighborhood. Okay, it's some neighborhood that contains all of these points we're talking about. So I have this. And then I have these quadratic error terms, so plus C h prime squared, 1 plus norm of Z over square root of n. Okay. Now this looks pretty good because I know this is small, and then there is this h prime I can play with. So perhaps, let me say, let us fix, let lambda be some parameter not too large. So not random, like a deterministic guy. But to be chosen, we'll see how to optimize it as we proceed. and choose. I'm going to choose h prime to be lambda times the sign of the, maybe I should write the sign of this difference of derivatives. Okay, and maybe let me allow myself not to write at t and hn. Okay, the sign of that difference. Okay, and I plug in. So what I get is lambda times absolute value. Okay, and maybe I should do several things at the same time. Okay, so when I replace, I get lambda times absolute value of this, bounded by the same thing with lambda square here. This is all very nice. And ultimately, I want to understand the expectation of the square of this guy. So let me also do that. Okay, let me also square it and take the expectation. Okay, so maybe I get, okay, maybe 8 times and then the expectation of the norm of v squared is n. So these two things match out. It's just a constant. And so I just get this. Maybe I could have written it like this then. Well, okay, whatever. I guess this. And we have an estimate for this. So, I mean, now when we are at this stage, we see that it feels pretty good, right? We wanted to estimate this difference of the derivatives, and we kind of managed to map it back to a question on the difference of the functions themselves. So now it's just unrolling, like observing that indeed we can declare victory. So we said we have an estimate. Maybe we've done the F-Ronstein, so we only know it's n to the minus 1/3 with a constant. So I'm going to choose lambda such that lambda square is of that order. So we choose lambda equals n to the minus 1/6. And what do we get if we do this? We are going to get, so you have a n to the minus 1/6 also on the left-hand side. Fn minus Fn bar squared. That this is bounded by C over n to the 1/6. Okay, and this is what we wanted. To check the conditions for being a viscosity solution, I would like to say, let me write a so here. The time derivative, so I want to see what happens when I plug my test function into the equation. And I forgot the square. So we are at the contact point, so the derivatives coincide between phi and Fn bar. And then we can use this statement that tells us that this is bounded by 1/n, the second derivative, plus that term. And 1/n times the second derivative, it's still here. The second derivative is bounded by a constant. So this is going to be c over n plus c over n to the 1/6. And so it tends to 0 as n goes to infinity. And on the left side, because phi is smooth, t and hn goes to th, we get our condition. So we conclude that in the limit, f indeed is a subsolution. Okay, and this is what I wanted to demonstrate. Are there questions on the argument? So perhaps one more point of comment I want to make is that in the more general case, which I had written here, when you only control the absolute value of the equation, you see that at least when you touch the function from above, really what you obtain is not just that you have the inequality, you obtain that it's equal to 0. So at least you can see that whenever you can touch the limit from above, this will be a point where you can say the equation is satisfied. Okay, and this will be, together with the convexity, these are the two ingredients that allow you to conclude in the general case. Yeah, I did not give you an entirely complete proof because of this issue with the domain having a boundary now, but essentially you have at least a very good idea of how you proceed to show that in the limit of large n, this free energy is going to converge to the solution to this partial differential equation. And I gave you statements of, I showed you that in many cases, these solutions can be expressed as variational formulas. And again, I gave you these statements in the context where there was no boundary on the parameters, but you can extend these results to our current setting. So let me say that we can show, one can show, or we can show Hopf-like formulas. Even in this setting with this boundary condition. So what you can get is that the solution, you can write it in this form. So psi of h plus h prime minus, and then if you recall, the Hopf-like formula features the convex dual of the nonlinearity. So here our nonlinearity is the square function. The convex dual of the square function is x squared over 4. So I'm going to have h prime squared over 40. Okay, in general, it's t times the convex dual of the nonlinearity applied to h prime over t. Okay. Okay, and from there, as with the Curie-Weiss model, this becomes a simple analysis exercise to study the properties of this object. And I recall that, I remind you that the time derivatives of the free energy are really the quantities we were interested in if we want to study the minimal mean square error, for instance. Okay, the minimal mean square error we had completely rephrased in terms of the expectation of x dot x bar squared or x dot x bar, depending on if we were looking at the minimal mean square error for x bar itself or for the matrix x bar transpose. Okay, so we can again appeal to the envelope theorem, that thing that tells us that, allows us to identify the derivative of this guy easily in terms of what happens here, and to this principle that if the limit, if you look at the point of differentiability of the limit, then the derivatives of the function are going to converge to the derivative of the limit. Okay, so maybe I should say that last part we have only justified in the context when all the functions were convex. And I told you they are convex, but I really did not give you even a hint of the proof. So it's true, but in fact, for justifying this, it's enough that you have a lower bound on the second derivative. And having a lower bound on the second derivative, in some sense, we already have seen in the argument. So you can just, massage a little bit the standard argument using this weaker statement. And so we will have that at every point of differentiability of the limit, the derivatives of the function converge to the derivatives of the limit. So we have fully succeeded, I would say, in identifying the behavior, the asymptotic behavior of the minimal mean square error for this problem. So maybe I could say another word on this. So for instance, let's assume that just to give you a taste for what you can read out of this. So it's more interesting in the case when the random variables you're considering are centered. If you like, you can imagine they are +1, -1, and with equal probability. In this case, you can verify that the function psi near the origin is like a parabola. So we have then psi of psi of h looks like c times h squared near h equals 0. And so really like in the Curie-Weiss model, for t small, you see that here you have a very sharp parabola hitting you here. And this is, let's say we look at h equals 0. It's also a parabola. So for t small, you're going to want to stick to choosing your optimal h prime to be 0. And then as t increases, at some point this parabola will become wider than the competing parabola for psi, and then suddenly you're going to want to have your optimal h prime move away from h prime equals 0. Okay? And so you can show, just like in the Curie-Weiss model, that there exists Tc, which is the point at which this parabola stops to win over this parabola. There exists Tc in 0 plus infinity, such that for t smaller than Tc, we have that, maybe I'm going to write like this, expectation of x dot x bar over n squared. This is the t derivative of the function. This is going to go to 0 as n tends to infinity for t small. Okay, so the minimal mean square error for the matrix is just as bad as it can be. And then for t larger than Tc, you have that expectation of x dot x bar over n squared converges to some number, something in 0 plus infinity. Okay, something strictly positive. Okay, and at some point, someone, maybe Chen-Lin, asked me what happens at t equals Tc. So you can think about all this in great detail, right? You can think about the envelope theorem, whether or not the transition will be continuous at t equals Tc will be related to the fact that as you decide that your favorite h prime is no longer 0, are you going to do it continuously, or are you going to jump to some place far away? Okay, and this is going to be the criterion for whether or not this transition is continuous, whether or not at t equals Tc, you're still at 0, or you already see something strictly positive. Okay, so I said when does this parabola wins over this parabola, but this is not really a parabola. And maybe it's going to start winning against this parabola using a point which is very far away from the origin. Okay, you know that for t sufficiently small, it's not going to occur, but maybe at some point it will occur. It's not necessarily near 0. Okay, so you can produce examples with both behaviors. What else did I want to say? Yeah, perhaps another important point, which I think also showed up in some talks that we have in the afternoon, is that these considerations, they are really about what is best possibly achievable. Okay, I'm looking over all possible estimators for our signal, but maybe they are extremely hard to calculate. Okay, so this is really the information theoretical limit on how much you can recover about the signal, but it does not tell you how to calculate it on your computer. And so people have spent a lot of time exploring how this best possible case compares with regular, like standard methods for trying to get the signal out of this noisy observation. So let's say a comparison with, so it's interesting to try to compare with algorithms, okay? And by algorithms, I mean algorithms that will run in polynomial time in n. So I do not guarantee you at all that you can compute the optimal estimator here, the conditional expectation, in a time that is polynomial in n. So in the notes, you will find a comparison with the perhaps the most simple, the simplest algorithm you can think of, which is we're observing this matrix x bar transpose multiplied by something plus w. And we're trying to recover this. So perhaps one thing you could do, which doesn't take too much time, is look at the eigenvalues and eigenfunctions of this matrix and see what happens. Okay? And in the notes, we go in details into exploring how this performs. Note that this algorithm is completely agnostic to how you have picked your vector x bar. Okay, it does not depend. Like if I tell you, oh, I picked x bar like Bernoulli, or if I picked x bar like uniform over the interval, the algorithm remains the same. While our calculations here, they really depend on this low Pn that we have chosen. You know, the function psi is really a function of the law of x bar 1. I think okay. And so in the notes, we explore different options for what the law of x bar 1 could be. And perhaps, as you might expect, if you take for x bar something which is really very nicely spread around the sphere, like for instance, okay, so in the assumptions, I stated that x bar 1, x bar n are IID, but you could also imagine that the whole vector x bar is uniformly distributed on the sphere. Or as a proxy for this, you could just decide that x bar 1 up to x bar n are IID Gaussian random variables. So these are not bounded, so they do not exactly fit into my assumptions, but you can work your way through making sure that everything works also in this case. Then what you're going to observe is that the performance of the spectral method actually matches the optimal performance as predicted by these theoretical limits. Okay, so you're like best possible if you just do the simple spectral method, if you have this kind of uniformly over the sphere sort of information on x bar. On the other hand, things are going to change if you take different laws for x bar. For instance, if it's +1 - 1, there is already a small difference that occurs, which is that if you plot how much error you do as a function of t, so when t is very small, of course, you make a lot of error. And maybe the optimal thing tells you that this is the error you can do. Maybe it's some shape like this. And the spectral method, on the other hand, when the x bar is +1 - 1, will transition at the same point, but we'll have a less good performance. Okay, so it can occur that the transition occurs at the exact same time, or at the exact same signal-to-noise ratio, but the nice algorithm performs less well than the optimal thing you can do. And even more drastic loss of performance can occur, let's say, for other choices of the law of x bar. And this perhaps you can have an intuition by considering the situation. So suppose I tell you that, sorry, yes. Suppose okay, so this is again not part of the assumption that I wrote down, but imagine I tell you that I put only one of the coordinates of x bar to be equal to 1 and all the others to be 0. Then surely you can find some tricks to leverage this, which are really efficient. But the spectral method does not use any trick related to the law, so it's not capable of doing this. So in the notes, we explore a situation which is a bit less radical, but where, let's say, each of these coordinates can be either +1 - 1 or 0, and we kind of push up the probability that it is 0. And we see what occurs, and we see that as we push it up close to 1, in fact, you start to have even a gap between these two curves in the sense that so the spectral method does always the same, like so. But the optimal possible method will, okay, for a while we still have a big error because there's nothing you can do, but then it will start to go to 0 before anything happens, even at the spectral method. Okay, so it will look like so. Does that make sense? So you can have really a gap between these two regimes where the spectral method doesn't give you any information on the signal, but the optimal thing would actually give you one. And in the notes, we only explore one possible algorithm, which is perhaps the simplest you can imagine. But people have thought about this a lot and have come up with lots of evidence that, in fact, this region is such that there is probably no polynomial time algorithm that will do anything decently good. You can basically not recover any information, even though it's information theoretically possible. Okay, so I'm not going to explore this. Of course, we don't know that P is different from NP, so it's difficult to phrase exactly what we mean by this. But in my opinion, people have come up with very convincing arguments in this direction. What else do I want to say? So yeah, I did not give you lots of references on this problem. For the specific problem of rank 1 matrix inference that I described to you, there were already several proofs available when I started to think about it. And so the statement I presented is not, I put some references in the notes, and there are really many, many different proofs. Except for most of them do not use PDEs, and it's totally fine, of course. And for me, the main motivation was to try to push techniques towards understanding spin glasses. But it so happens that also with PD techniques, you can cover, in fact, a wider range of settings also in the case of statistical inference. So I mentioned that maybe instead of X bar transpose, you're observing X bar, Y bar transpose. This also has been studied with lots of methods. And again, PD techniques can handle them, but it's not the only technique you can use. But you can continue to try to generalize this maybe to, so these are like pairwise interactions in your observation. You can start to imagine maybe more than pairwise interaction, maybe a bit like if those of you know spin glasses, like p-spin sort of things, like maybe there are 3-term interactions in your observations or more, or other things you can do, which perhaps are meaningful from the point of view of community detection, is that maybe you have a bunch of people that you want to understand properties of them, how they organize into different communities, and you don't have only one social network that you observe. You have several of them. So you have a multi-view sort of problem. You have different observations that take different structures. How you combine them? As the more you complexify the problem, the more I think PD techniques have a better chance to succeed in handling them. So the paper where we try to write down a setup in which we try to, which we try to be as general as possible, is a work that we've done with Hongbin Chen and Jiaming Xia and myself. Yes, so you can have a look if you like. For me, so perhaps a word on other like open questions, like things that are not well understood. So in this context, for instance, you can consider not just rank 1, but maybe finite rank situations when X bar and Y bar are not just vectors, but they have a little bit of a width. They have another parameter k here, which maybe you think of as fixed, so that you can describe finite rank instead of rank 1 matrices. And one thing that people have been wondering about is what happens if you try to let the rank diverge as n tends to infinity. Okay, can you control the behavior and these sort of things? So there are some results in the literature, but I think maybe PD techniques allow to get better estimates on, or even if you keep k fixed. Here I gave you qualitative statements of convergence, but maybe you want to understand rates of convergence. And again, I think PD techniques are kind of handy to try to estimate these rates of convergence rather sharply. So for me, the most, again, my interest is a little bit biased towards spin glasses. So I was extremely curious about a situation which, again, maybe we can talk about using this community detection analogy. So for the problems I described here, the community detection is a problem that you can map into the problem we studied, as long as the average degree of each node diverges as n tends to infinity. But you can also try to understand what happens when this is not the case. When your graph is like, okay, you have a random graph with this community structure built into it, but the average degree remains bounded as n goes to infinity. And there, the situation is very analogous to the spin glass situation. There are, I can write a PDE which is plausibly the limit. I can write an inequality between the limit free energy and that solution to that PDE. And we can also state this result about critical points, blah, 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 which I'll try to phrase more precisely tomorrow. But there is no, okay, depending on the model, but for some models, at least, there is no perfect characterization of the limit free energy in this case. And perhaps the message is that as long as something is convex in your problem, you're in good shape. If the nonlinearity in the equation is convex or concave, then things will be fine. If the function you're studying is convex or concave, then things will be fine. What breaks down, so here in these statistical inference problems, the functions are convex. I did not show it, but it's true. And this is really what allows us to solve any problem that comes about. But when you move to the sparse setting, for reasons that surprised me, it so happens that the function that you want to study is not convex, in fact. So I don't know what to do in this case. Yeah, perhaps one last word of comment, and I will stop here, is I spent a lot of time discussing Curie-Weiss models at the beginning, and I think it's interesting to think about these generalized versions, because I'm not sure if I know other ways to find the limit of the generalized Curie-Weiss model than those I gave to you, in fact, the large deviation principle and the PD technique. So I think, well, okay, maybe I haven't thought about this carefully enough, but if you have candidates for other techniques, I'd be happy to see if they work on this case, and if they do, please let me know. Yeah, so I'm a little bit in advance, but okay, that's all I had planned to say today. So yeah, let's resume tomorrow for spin glasses.